Thank you, Sami, also for the invitation and for this great achievement. It's an honor to be here at the birth of the School of Robotics here, and already the excellent lineup of speakers to this event shows that this place is recognized and will have, I'm sure, great success in the future. I will be speaking about drones today, so it's the last talk, I understand. Oh, Sam is speaking after me, actually. But I will be focusing about on drones and on how biological inspiration can actually lead to applications and companies in the real world and make an impact. This is an artistic rendering of where we want to go in my lab, and you see a few topics that we touch. I won't mention all of these in these 20 minutes, but what we do is that we take inspiration from nature for the mechanics and the materials of these machines. We look at the sensors and the perception and the control, and we look how these machines work together, and especially how they fly in built environments and near humans, so also the human-robot interaction. Today I will focus on the perception. I will focus on the mechanical design and on the human-robot interaction. I won't talk about the swarms, which is another topic I'm very interested in, but I won't have enough time. So when I started off with my students, I was looking for a challenging problem in robotics. I was doing evolutionary robotics, biologically inspired robots, neural networks, and that was the time 2004, 2005, the second winter of neural networks. I couldn't find any more funding for neural networks. And I was working with robots, and I was looking for a challenging problem where biologically inspired perception or control could solve problems that we couldn't solve otherwise. And I was looking at drones. And all the drones at that time were huge machines flying high in the sky using GPS, waypoint navigation, and they could not fly in cities and near us. Why not? Because there was not sufficiently small perceptual system that could rapidly make these drones contextually aware. And I thought this is a place where, indeed, biological inspiration could come up with solution for perception and control. And so I tapped on 50 years of knowledge in neurophysiology that people in Germany and in France and in Australia and many other places had gathered about how the functioning of the insect vision system. And after 50 years of research, it turns out that insects use these compound eyes. So multiple eyes looking in multiple directions, and there are only 3 synapses that connect the information that goes into these eyes in movements of their wings. So something very fast happens there, allows these insects to avoid obstacles, maintain altitude, find their nest, find their mates, find food, a lot of different things. So we started to look at that, and we've made a first rudimentary copy back to 2007, 2009 of a compound camera. So this is the front view of a fixed-wing drone, and you see multiple cameras pointing in different directions, just like insect eyes, pointing in the directions where they have to look at. For example, the frontal-looking camera looks at the ground, and cameras on the sides look on the horizontal plane, so they can avoid obstacles, and they can also avoid the ground. And beside these cameras, there are neuromorphic chips that detect motion just like insects do, and connect with very few lines of codes. It was, I believe it was something like 70 lines of codes. Connects the input of this motion in a biologically inspired ways to the control of this drone, so that the drone can, as it flies, using only this camera, can maintain altitude, avoid any obstacles on its flight. And as you see, as it falls down because of gravity, there is no obstacles. It sees the ground, and it avoids the ground, so automatically it also maintains altitude. So very simple set of instruction lines. Today we can do this with deep learning, of course, but still there is an advantage because we have a very simple code that runs super fast on these cameras, and that point in many different directions. So at that time, we thought, okay, how could we possibly use this technology for real drones that can solve problems? And we started a company, it was back in 2009, called SenseFly. And at that time, and still today, most of the drones must be piloted by humans. So you use a remote control for safety reasons. But one of the problems that these drones have is once they've completed the mission, imagine that the operator is here, you must land the drones. And landing the drone is very difficult because you must make them land near you, especially if you have fixed-wing drones, not quadcopters. you must make sure that they land close to you. Now, GPS is very good on the X and Y coordinates, but on the vertical line is not sufficiently precise. So very often you tend to crash these drones if you're not careful with the landing. So what we did is that we used that optic flow detection, biologically inspired optic flow detection, in a set of sensors under the belly of the drone, so that when the drone arrives where the operator is, it flies back approximately 50 meters from the operator, and then it initiates an automatic landing using a fusion of GPS information, and then switching on the optic flow landing, just like insects do, so slowing down, pitching up, and we could guarantee landing, safe landing within 5 meters of the user. So the company SenseFly, which has since then been acquired by Parrot, has produced a number of different drones. You see the EB there, we used mainly for cartography and imaging. The new machine is no longer called Exom, it has a new name, but Albris is used also for inspection. And they widely use this optic flow detection for maintaining distance from objects and safe landing. Now, okay, how can we further miniaturize these cameras and make a compound eye just like those of an insect? An insect has a Drosophila, like a fruit fly, has approximately 700 eyes, compound eyes. The compound eye is made of approximately 700 eyes. And so together with a team of people at the Fraunhofer here in Germany, Marseille in France, we built the first artificial compound eye, which you see here. It's made of 700 eyes. It has a total weight of less than a gram. It's only the black stripe that you see there. And it has a thickness of less than a millimeter. Now you say, well, it's still larger than an eye, than the eye of an insect. Yes, it is true. It's not spherical. Yes, it's true. It's still a cylindrical eye. But the important thing is that each of those eyes has exactly the same circuitry that most of the flies, honeybees, bumblebees, large insects use, and it does the same sort of computation, and so it can perform the same type of flight maneuvers that those insects do. Larger, but since we are using electronics, we can be 4 times faster than insects are. So we can use this technology now for flying much faster than insects do and have the same resolution. Now it turns out that when we were doing this work, a paper came up in Nature where the first evidence of a compound eye in nature was used by trilobites living between 250 million and 500 million years ago on the floor of the oceans, and they had a cylindrical eye just like our compound eye. So if you give us a few million years, I'm sure we're going to get very close down to the insect. But no matter how good your perceptual system is, if you want to send this machine, these small drones, today they are very small, into situations like this is the Fukushima reactor disaster, sooner or later those drones will collide with cables, with sticks, because they won't be able to detect them. They will fall on the ground, catastrophic situation, the drone is on the ground, who goes back and puts it up or replaces it? At that time, I sent one of my brilliant master students to my colleague Rob Wood at Harvard to create a miniaturized camera system to study how flies fly in very cluttered environment. And when the student, Adrien Priot, came back, and he showed to me the videos that he flew, I was struck, because it turns out that these flies, when they fly in very confined environments, they stop avoiding things, and they just bump into obstacles all the time. And compared to our drones, what happens is that first, when they collide, they don't break because their exoskeleton and eyes are flexible, they absorb the collision. Second, they use their legs to upright themselves, both in flight, to stabilize themselves, and when they are on the ground, to upright themselves. So we said, okay, we could make collision-resilient drones that can fly around, have a shell that protects their body, so when they fall on the ground, they don't break, and then they deploy legs to upright themselves again and fly. So essentially, this is a drone that has almost no perceptual system. It is only attracted by the light at the end. And what it does is that it leverages its embodiment to fly against obstacles and fly towards the light. Okay, it's nice, it doesn't break, but it's not really the most efficient system that you can imagine. It falls all the time, and that's not energetically very efficient. Why does it fall? It falls because whenever there is a collision, the propulsion system of the drone is destabilized, and a velocity is generated in the opposite direction of where you want to fly it. And if this destabilization is too large, then the drone will eventually fall on the ground. And so with my students, we thought, well, okay, how can we possibly achieve the capability of students to stabilize? Let's do something which is not biologically, it's not mimicry, but serves the same purposes. So we added an external passive gimbal to this drone, which allows the drone to absorb the collision and essentially slide against the obstacle, while the internal propulsion systems remains extremely stable. So it's completely passive, it's super simple, and we said, hey, here we have the first drone that we can send anywhere, is collision resilient, and can fly in very confined spaces. And so we create a company, second spin-off company called Flyability, which makes collision-resilient drones for inspection of confined environments.
The world's first collision-tolerant drone. Access confined and complex spaces without any risk of crashing. Helios features a full HD camera and a thermal camera embedded on the drone. The robot's live video feed allows the operator to get the drone to the most inaccessible places up to 5 kilometers when in direct line of sight. Gather close-up images for high-resolution data with a sub-millimeter resolution. Onboard LED lighting system and a complete remote control of the camera settings allows to navigate and inspect even in pitch-dark environments.
Just want to show you some features in a moment.
Changing the batteries only takes seconds. Just unplug the used one, insert another of the provided batteries, and you are back to flying again. Helios is safe to fly close and even in contact with humans.
So you see, now we can start to have human-drone interaction because the drone is extremely safe. And this opens an entirely new avenue of research of how we can work together with machines which are non-anthropomorphic. Now, let's move on to a different topic. So these drones have relatively small payload capacity. So they can typically carry sensors. So when you think about, okay, let's use robots to do heavy work in the environment, for example, lifting heavy weights, then immediately you think, okay, we need powerful machines like humanoid robots that can lift these heavy weights. But again, if you look at biology, you see that there are also tiny animals, like wasps, this is the killer wasp, which can lift weights which are much larger than their weight. And the way in which they do that is that they exploit the environment to attach themselves and then pull up their prey to the position they want. So they do not necessarily fly with the prey, but they exploit the environment to do this heavy lifting. And so with my colleagues at Stanford University, we look at the possibility of copying or sort of getting inspiration from this mechanism, and we use these macro spines from Kutkowski lab placed at the bottom of these drones, so that these drones, what they can essentially do is that they can attach to a heavy payload like this one with a specialized end effector. Then what they can do is that they can fly to an elevated surface, they land on the surface, and then thanks to this microspine, they exert a lot of friction, and then they have a winch which is used to lift this heavy load. Now, if you manufacture these attachment points appropriately, and you put many of these drones together, you can do amazing things, like, for example, using 2 drones to open a door. We call them forceful manipulation. So you have a first drone, which has a specialized end effector, which allows the drones to go down on the ground, slips this sort of hinge under the door, then goes there, it attaches with the microspines on the carpet, and from there it can use the winch to pull the door. There is another drone then that has a handle, that has attachment to the handle, attaches to the handle, goes on the ground, and then it puts, as you will see, an adhesion against the glass, and then it will pull again with the winch against the handle, and the coordinated motion of the two allow these drones to open the door. So, of course, this was remotely controlled, this operation, but it shows you in the principle that we can take inspiration from nature to create machines that can do amazing things. Now, okay, you say, well, they were not really flying. Possibly the next killer application of drones, as you have heard, is delivery by drones. Now, this picture has already been told, all these pictures, but there are many companies that are thinking about drone delivery. Now, there is a fundamental law of physics, aerodynamics, that is such that if you want to transport or lift heavy loads, then you must have a large drone. Why is that? Because the lift capacity of the drone is proportional to the product of the air speed against the aerial surface, that is the propellers, how fast the propellers turn, or how fast the drone moves in the air, times the surface of the aerial structures. That means the size of the propellers or the size of the wings. So there are only two options. Either you make these drones fly faster or spin the propeller faster in order to lift heavier weights, or you make the propellers or the drones, the wings, larger. And because there is a limit in how fast you can fly drones in built environments or near humans, what all researchers and companies end up doing is making larger drones for lifting heavier weights. And this creates a problem because these drones are dangerous. The propellers are large. They require quite a lot of infrastructure. And so these typically delivery drones are used in two ways. Either they're used to connect two logistics centers where the people who can handle these drones when they land and take off are professionally trained to go there and operate these drones, or you have these drones that deliver blood, for example, of parcels by pulling them, letting them going down with a rope, or simply using a parachute to lift, to launch the parcel at the right location. Is this delivery? Yes, it may be delivery, but if you think about delivery the way in which we experience it every day, this is delivery. It's hand in hand, right? How can we make drones that can deliver parcels to the person, what I call last centimeter drone? We need to do two things. We need to do first to protect the recipient, the person receiving the parcel, from the spinning propellers. Second, we must make sure that the drone, when it is not used and sitting in the van of the postman or in the motorbike or the postman, is sufficiently small so that it does not occupy 10 times the size of the parcel, right? So again, we can look at nature. And in nature, the wings, when they are not used, they are put back in place, so they are folded. They are unfolded very rapidly, and then they are folded back. So we did a lot of research in folding drones like this. I will show to you an example now in the field of delivery. Probably the next big use of drones is delivery. However, because of the laws of physics, the heavier the parcel is, the larger the drone must be. And this creates two problems. The first problem is that it is very hard to store these very large drones and to transport them. The second problem is because of the large propellers, they become very dangerous for people. So with this new drone, we have solved these two problems at the same time. Here, this new concept, the drone becomes the package. When the package is folded, it's very small and you can store and transport it. When the package is unfolded around the parcel, it provides protection for the people, so they don't get cut, and it also provides protection for the parcel. The challenge to this. So what we did is that in addition to the mechanical design of the drone, there is also all the software that allows this drone to fly in built environments. I won't cover it with the camera and so forth. But what we did is that this, we spin off a third company, excuse me. This is for last centimeter delivery. I would like to have something like the WhatsApp of things. You have your drone in your parcel. Somebody tells you, hey, Dario, send me this stuff that you have. And, okay, I can send it. I can take the drone out, put the stuff in, and then up the drone flies and goes to you, and you just grab it by the hand, and then the drone goes back, or you keep the drone. There are different models. So last year on campus, we let students order 3D printed parts or 3D printed electronic circuits from the workshops using drones. So if the parcel was if the piece was sufficiently small, the students used our standard interface to order the part. And then if the part is small, it's written drone delivery available. They click on it. All they have to do is download an app. And when the part was ready, the technician took the drone out of the drawer, put the part into it, said it's ready. The student receives notification on the app. The technician takes the drone outside of the window, lets the drone go, and the drone flies. You see a typical path of the drone flying towards the person receiving down there the drone in the hands. So this was very interesting, and what we realized is that there were a lot of problems, not with the drone itself, not with the navigation, but when the drone arrives, the person doesn't know what to do. And he starts manipulating this drone, so what we realized is that there is a big opportunity for human-drone interaction. So the drone talks to the person manipulates the drone feels with sensors what the person is doing, and therefore does a number of different things. Let me go to the last 2 minutes of presentation. So I mentioned many times human-drone interaction. I am a terrible pilot. After 15 years of almost researching drones, I still crash all the drones. And if you look today, state-of-the-art in drone control is first-person view drone racing, where you've got these kids, the champions today are kids 15, 16 years old. And they use all these remote controls. They have the image coming from the camera of the drones in their eyes. It's extremely difficult. You can do it, but I asked them, I organized the national championship at EPFL for drone racing, and I asked them, is it like flying? Do you feel like flying? They said, no, it's just like playing video games with cars. And then I thought, okay, maybe here we should make everybody capable of flying. But I was also interested in, could we make a person become the drone? Could we make the person change its own body into a non-anthropomorphic body and naturally fly as if the person was a drone? And so I thought, well, we could have a human-drone symbiosis by using wearable technologies that create an intuitive immersive mapping between a human body and a non-anthropomorphic body using bidirectional information between the person body and the drone. And the first question we had to ask was, okay, how would a human fly if the persons could fly? We don't fly. So we said, okay, first thing we did is that with my colleague Silvestro Micera, at the Campus Biotech in Switzerland, in Geneva, we put a number of subjects around the motion capture system. We filled the subject with motion capture, with the mock-up that was described this morning, muscle activity sensors, and we pre-recorded sequences from the cameras of drones flying, and we played back the sequences seen from the drone into the person's eyes, and we asked the person, try to move your body to replicate what you see. We didn't say there is a drone flying out there. Try just to reproduce. And so the person would start to do all sorts of movements, and we would record what the person was doing. And we thought, this is crazy. We were not going to get anything out of this. Amazing. 85% of the population flies using the same type of body motion. And so what we did is that using the machine learning, we took all the data, we extracted this body motion. Most of the people, what they do is that they spread their arms out, and then it's a combination of torso pitch and rotation. Now the arms out, after some time, they start to put the arms down because they become fatigued. They are not really used, but it's sort of expectation that you have to spread the arms out. It turns out the arms out help a lot to do fine control because you can have proprioception, very fine proprioceptive information about the tips of your arms with millimetric precision on the torso. So in any case, we extracted the motion of the body, and then we created a flight jacket, which is a soft exoskeleton up their torso, which gives the arm support to the person, allows us to put inertial measurement units on the body exactly to track what we need to track. We have a virtual reality headset, and what we can do is that we take the same inferred strategy for controlling the drone, we put it on a person, and we let this person fly a drone. Now, you will say, okay, that's fine here. So the first thing is that we realized is that the persons immediately, you never flown a drone, you put on this thing, you immediately fly a drone with the precision of a person that has been trained for 7 days. Absolutely amazing. And if you are, maybe some subjects are not so good, they take a few minutes to be perfect with the drone. But the other good thing is that the hands are free, and hands are very precious real estate on our body. And so now we can use data glove to give additional commands to the drone. We can use, for example, combination of finger touch using the data glove to make the drone take off. Other combinations of finger touch allows the person flying the real drone to position on a map a point. So for example, you see the person is flying there, and then this is what the person is looking as it flies, and then suddenly this person says, okay, here there is a point of interest, and as soon as there is a point of interest, it will touch the fingers, you will see in a moment, and the other person looking at the map in real time will see this point appear. And this could be used, for example, by firefighters to do very quick reconnaissance of, for example, an area. You see here a point has appeared. The person can see the point there as it flies. The person puts a second point there. Red means danger. For example, green means come here. So we can immediately populate a map. So you can see, or you can imagine, you can play games with this. But amazingly, the incredible thing is that you become immersed, you become a drone. The person don't feel like they are controlling a drone, person feel they are flying a drone. And a very great success that we had recently is that Jetman, the first and the only flying man today with the wing strapped on its back, with the reactors, heard about this, came to the lab. We were a bit nervous, and he said, so you say that you fly like naturally, like I fly with my body. Let's see if it's the same thing. He put the jacket on and immediately flew. We could see in the virtual reality where he was flying. He could fly immediately naturally. And as he was flying, he said, I don't know what you did, but this is exactly the way in which I fly in the air. I want to conclude with this, and I want to say only one thing. What is the future? In my opinion, as we have seen many talks also this morning and this afternoon, the future is robots becoming more interactive, going towards the physical world, even drones, interacting with the drone. And I really believe that the human-robot symbiosis is the future. It is the technologies that we are measuring on the body, the neuroprosthetics activities that we have, all the knowledge of the brain. I see more and more, and culturally, all the kids today, they have no problems with living and working with drones. I think the symbiosis between the humans and the robots is the future. I want to conclude by congratulate the Technical University of Munich and Sami. Let's fly together. This is a great adventure. Let's enjoy. Thank you.